I'll share my screen. Can you all see my screen?
Yes, sir.
Yeah. Okay. All right. So finally, we are going to talk about certain connectivity analysis methods. They are similar to what we had seen earlier in the case of LFP, but in the case of EEG, there are some other things that are also used for reasons that I will mention. So we'll talk about that first, and then we'll quickly talk about Granger causality, and that's it. That's how we'll finish. Okay, so all of these are already implemented in one of the MATLAB codes that's provided to you, display connectivity. So you just have to run that program and choose one of these options, and it will plot you that. I'll show you those plots here as well. Okay, so this is related to the question that first I found out where the gamma sources are. That was the previous question to which we, did source localization and all that. And now another question could be that, okay, there's a gamma source here and maybe certain other sources somewhere. Then, are these brain regions somehow talking to each other? So what's the connectivity profile between one brain region and another when a particular task is being done? It's a very important question because you will want to know how different parts of the brain are communicating to do a particular cognitive task. And in this case, we won't solve it in the source space, although the techniques would be very similar for that also. We'll do it in the sensor space. So you've got data from 64 channels, and you see that certain electrodes show a lot of gamma. So now I want to know if I have any measure of phase consistency across electrode pairs, what would I get? Okay, and are there certain other areas which show higher um, connectivity as measured by phase coherence, for example? So how would I answer that? So let's look at one electrode. This is electrode 61. So this is the one I had showed earlier. Green is baseline and black is the stimulus period. So there's a huge buildup of gamma oscillation at around 30 hertz in this case. There's a suppression of alpha as well. So you could compute the coherence between this electrode and all the other electrodes. Okay, that's straightforward. And you'll get something that looks like this. So here I have, and this is what you get from field trip. So you can see that each of these traces is the coherence between the electrode 61 and that particular electrode. Okay, so it's placed at the location. So 61 is trivially 1 at all frequencies. So I'm not showing that. Uh, but you will get a phase coherence profile which will look like this. And notice that electrodes that are close to this particular electrode are almost coherent at all frequencies. This P3, P1, you can see it remains very, very high at all frequencies. So why is that? Anyone? Are you guys able to see these plots?
Yes, sir.
Okay. So why is the coherence at P3 almost close to 1 at all frequencies? Anyone? I mean, you can guess. It's not a very hard question.
Coherence between P3 and which electrode?
P1, sorry, P3 and this electrode 61,
Electrode 61.
this one.
Oh, they are very near. Is it so?
Huh, so why should it be high if it's very near?
Nearby electrons, electrodes do have a high coherence. They are just giving you the similar signals.
They pick up the similar signals. That's right. So this is called volume conduction. This basically there are certain sources buried in the brain that are producing some measurable signal on the scalp that's being picked up by these sensors. And generally, especially in the case of EEG, there could be just a few dipoles or big synchronous dipoles that are producing these signals. So essentially, all the electrodes are picking up the same signal. Okay, and therefore the correlation, the coherence or phase consistency is trivially very high. This is because they are not picking up different sources, they are actually picking up the same source. Okay, so this is a problem, a well-known problem called volume conduction, which means that it's not, the same source is getting picked up at many different locations. This is true for all signals, but especially true for EEG because the sensors are quite far from where the sources are. So only very dominant sources produce these dominant signals on the sensor space. So each sensor is essentially picking up very similar activity. So coherence is very high. So how do we address that? Well, one solution that you may think of is that I change my referencing scheme so that the common signal that is being picked up somehow gets cancelled out. So you could try doing average reference as shown here. And now the average reference does show some change, although it still remains pretty high, but it's not as much as before. And also there's another part here which starts to show some more signal. The topo plot here is between the gamma range. Okay, so I'm just, yes, I could show you the MATLAB plots. You can see how these are being plotted. So this is display connectivity.m, and here you can choose between the method coherence, imaginary coherence, weighted PLI or PPC, and mention the remaining ones. So let me just run this. So display connectivity. Okay, so this is the same plot that you had seen. Here I have chosen the reference type to be unipolar. You could have done average here as well. And now if I, let's say, want to look at a particular electrode, I would just do this. This is the C1 electrode and I click on that. and then I choose between 25 to 35, and this gives the topo plot of the power between 25 and 35. That this is what I was showing here. Okay, it's the same as this plot here. And if you chose average reference, then you would end up getting this plot. So this is how gamma power is distributed. Gamma coherence is distributed along the scale. Okay, and this is a common problem that even after average referencing, you'll end up getting a lot of similarity at nearby electrodes wherever you are starting from, just because of some common signal that still didn't get cancelled out. So just simply doing a referencing may not be enough, although it does tend to improve and show that another region here that is has a peak there that shows up in this analysis when you do average referencing. So coherence can be biased by presence of a common reference, because every signal is a reference to the same reference, volume conduction, common noise, sample size bias. I'll talk you about the fourth one. So these are the issues that I need to deal with in order to get a better understanding of real sort of phase consistency, not artifactual ones which are produced by all these things. So the remaining strategies that I'm going to tell you, remaining solutions, sort of tend to address these issues, the common, volume conduction related issues. And one method will deal with this sample size bias that I'll talk to you about in a bit. Okay, so what I showed you here was just the coherence, this plot, with respect to one electrode, electrode 61. And I chose that 61 electrode because that had a very strong gamma. As you can see here, it's very strong gamma. But you could actually do this analysis for each electrode. Each electrode could be the seed region, and you could then get a topo plot like this for that particular region. So how do I display this whole thing? One way is to make plots like these, where can you guys see a black dot here? It's maybe hard to see. So there's actually a black dot here, which is the seed region. Okay, so this is the electrode here, and the black dots are all on this side. It's hard to see because it's very reddish there, quite trivially, because whenever you pick up electrodes, whenever you look at electrodes close to the seed electrode, the electrode with respect to which you are computing coherence, those electrodes will have a strong component. Okay, so this is the coherence, topo plot of topo plots in the alpha range for one subject. This is just a way of displaying data. And wherever you look at, whichever electrode you look at as the seed, coherence is quite high nearby in the nearby electrodes. So one solution that's given by Nolte is very straightforward, and that is that if you look at volume conduction, in which different electrodes pick up the activity of the same source, then the phase difference ought to be 0 between them. The signals, if I pick up from two different electrodes that are nearby, have to be exactly the same. So if this is one electrode and this is a scaled version of this, so there is some source and two electrodes E1 and E2 are picking up the same activity, noisy versions of the same activity, then they will actually be at the same phase. So when I look at this, so remember when we were looking at coherence, we were looking at vectors. Each trial gave a vector, and the idea there is that if different electrodes are phase consistent, then the vectors all point in the same direction. Doesn't matter what the direction is, they all point in the same direction. And coherence is nothing but the average of that, modulus of the average normalized by the length of the vector. We can talk about phase coherence, in which each vector is of unit length. So if something is random, they point all over the place, and then the resultant vector is very small. Otherwise, the resultant vector is very large. That's how we computed coherence. Now, what this guy is saying, Nolte is saying, is that what we should look at, if this is the final vector, which is the average of all the vectors, we should look at the imaginary component of that. That's it. The logic being that what you see along this axis could just be because of volume conduction. But because of volume conduction, you can never have a case that two electrodes pick up activity which has shifted in phase. This could never happen. I mean, you have to ignore certain things like the time derivatives in the Maxwell equations, which could cause some phase difference. But using standard quasi-static approximation, you can never have two signals that are phase shifted when they are representing the same source. So the imaginary component could be a way of looking at phase consistency, which is not because of volume conduction. Okay, so phase shift in frequency domain corresponds to a time lag in time domain. The imaginary part of coherency is insensitive to artifactual self-interaction caused by volume conduction, because a signal cannot be time lagged to itself. So it's a very simple solution. You compute the coherency, which is a complex number. The modulus of coherency is coherence, which I looked at here in all these plots. But instead of the modulus, you look at the imaginary part. And that is what imaginary coherence is. And then the plots, the same plot here, reduced to something like this. Now you can see the black dots also here. So the imaginary coherence plots show something different. Okay, now you see that there's another problem here, that the nearby electrodes are always close to zero. And that is where there, even if there's real signal, sort of interactions that are going on, they will get set to zero because the phase difference would be close to zero. So the vectors will all be pointing along the real line, along the real axis, not the imaginary axis. So you see a bunch of green around each of these electrodes here. Green corresponds to zero. Okay, does this make sense? The imaginary coherence? So just to make sure that everybody on track, I will just briefly again refresh the memory of what coherence is. Coherence is, I'll talk about phase coherence. Phase coherence basically means that you look at the signal, a particular frequency of the signal. So at a particular frequency, you have a amplitude and a phase. And between two electrodes, you are only going to look at the cross spectrum, which is AF, BF, e to the power j phi f minus theta f. Here phi and A correspond to electrode 1, B and theta correspond to electrode 2. We will only deal with phase coherence, so we will remove this, and we are going to just look at this. So this is just a vector, unit vector pointing at some direction, theta minus phi, which is the phase difference between the two. Each trial gives you one vector, and coherency is just the average of these vectors. When trials are all vectors are all over the place, this is very small magnitude, otherwise it has large magnitude. So this is coherency, and earlier the phase coherence is just the modulus of this small vector, so it's the size of this vector. Imaginary coherence is just the imaginary component of this vector. That's the only difference. Okay, and trivially, if all the vectors are pointing in this direction, which is what you would get because of volume conduction, your resultant vector will also point in this direction, and then the imaginary part will be 0. So this will wipe out any contribution which is because of volume conduction. But unfortunately, it also wipes out contribution, any sort of phase relationship which is physiological, not because of volume conduction, but happens to be at the um, same phase, so that the phase difference is 0. It will wipe that out as well. So in our data, if I compute coherency, it looks like this. But in the MATLAB code, now if you change coherency to, the method from coherence to IMC, which is the imaginary part of coherence, it looks like this. Okay, and now you can see that it's picking out some activity. This is again with respect to this electrode here, electrode 61. It's picking out some activity which is somewhat farther away, near the central part of the brain. Okay, so this is imaginary coherency. Any questions on this? Does this make sense? I'm going to sort of keep building on this stuff. So if you are confused or have any questions, even if it's a silly one, please ask. Okay, so then I will march forward and tell you about the issues with imaginary coherence. One issue obviously is that the magnitude of this imaginary component not only depends on the amplitudes of the signals, but it also depends on the magnitude of the phase delay. So it's most effective when phase lag corresponds to 90 degrees, quarter of a cycle. But if two signals are completely in phase, so the vectors looks like this, or out of phase even, so that it looks like that, then also the imaginary component is 0. And this is absurd because, can't be out of phase because of volume conduction either. So unfortunately, you need to have vectors that are pointing in this direction to have a strong imaginary coherence. So this is also sort of biased in this case. So a new idea was proposed by Stam and colleagues, which is called the phase lag index. And there the idea is that you don't really care about the magnitude of this, this imaginary component. You actually look at the asymmetry in the distribution of instantaneous phase difference between two signals, which means I'm going to look at signals. These are these different vectors for each trial, and I'm going to simply ask how many are positive and how many are negative. I really don't care if they are all like this versus all like that. Okay, so this magnitude of the angle is made irrelevant. I'm just going to check how many of them are positive and how many of them are negative. That's it. So if they are equally spread out, so that some are positive and some are negative, so the distribution is uniform. So I will say there is no interaction, PLI will be 0. Otherwise, if there's a systematic change in the distribution on one side, so more on this side, less on that side, then the PLI will be non-zero. Okay, but I don't care whether they are small, slightly shifted or really shifted. I don't care whether the vectors point in these directions, vectors point in this direction versus that direction. They'll both be positive. Okay, so I work now with the sign of the phase, not the magnitude of the phase or the magnitude of the cosine. Sorry, or the sign of the signal. It's just the the sign, whether it's positive or negative. That's the only thing I care about. Okay. So let me read this out. The PLI estimates for a particular frequency is to what extent the phase leads and lags between signals. So I'm just going to check whether to what extent the phase leads and phase lags are non-equiprobable, irrespective of the magnitude of these phase leads and lags. Okay, I'm just asking in how many, let's say I've got 100 trials, how many have a phase lead and how many have a phase lag? If it's 50-50, then, then there is no PLI is small. If it's away from 50-50, then you get a measurable signal. Okay, so we're essentially discarding phase difference that are centered around zero. And one way to do this is to define an asymmetry index for the distribution of phase differences. And if there is no phase coupling, then this distribution is expected to be flat around zero, and otherwise there's going to be a deviation. So mathematically, this is what it is. So phase coherence, remember here, this is a vector. Okay, so one vector, and this average is the average of all the vector. Each trial gives me a vector. So earlier phase coherence was simply the average of these vectors and then the magnitude of that. Phase lag index or PLI is that you look at the change, this delta phi, and you look at the sign of this. Now the sign of this is either +1 or -1. Okay, if it's positive, it's +1, otherwise it's -1. And I'm simply averaging the signs. That's it. Okay, so any questions on PLI? Conceptually, it's very straightforward. I just take the sign and then I average the signs. So if there are half of them are positive and half of them are negative, the sign, the average here, this is the average, so expectation is written like this. So the average is going to be close to zero. So the PLI is going to be small. But if all the vectors are pointing in the same direction, which is different from zero, so all of these are positive. So PLI is now going to be very large. And it won't matter if all the vectors are like this, or they are all like that, or they are all like that. These will have the same PLI. Even though the IMC is going to be different, it's going to be largest for these and smaller for these. Okay. So everybody happy with PLI? Say something, guys. Is this okay? Now I'm going to tell you another version of PLI. Just okay, so Okay, I'll move on. So one issue with PLI is that there's the so when you are very close to zero, a vector like this versus a vector like that. So this vector has a contribution of +1. This vector has a contribution of -1 because I'm looking at just the sign of the angle. So if the actual phase difference between two signals is sort of close to zero, then a little bit of noise can actually have a very big effect. Okay, so this index is discontinuous around zero. A little bit on this side makes it +1 and a little bit on that side makes it -1. So it's very sensitive to noise when the actual phase difference between two signals is close to zero. So one way to address this problem is to actually work with the signs as before, but then you are going to multiply this, weight it by the imaginary part of the the vector. So you might be wondering, are we going back to the imaginary coherence? No, we are not, but it's actually again somewhat comparable. It's basically weighting the contribution of the sign with the imaginary part. So it's similar but not the same. The WPLI looks like this. So if X is the cross spectrum, I denote this as the imaginary part. So I am looking at the sign of the imaginary part here. But now I am multiplying it with the magnitude of the imaginary part. So if I have got a vector which is very close to zero, it's going to get scaled by a small number. So its contribution is going to be somewhat less. The sign of this is going to be somewhat less. Okay. And then I'm going to also normalize it by the magnitudes of these imaginary components. And this is the weighted PLI. If I didn't have this, it would have reduced to just the PLI. PLI is just the expected value of the sign of the imaginary part of X. Right, so the imaginary part is positive here and negative here. So I can just look at the sign instead of the delta phi, I can just look at the imaginary part. But I'm scaling it by the magnitude of the imaginary component and then normalizing it by the average of these magnitudes, and this is the WPLI. Okay, so it is a nice way to alleviate the discontinuity because the vectors that are very close to zero have a small imaginary component, so their contribution is less. Okay, so it is somewhat comparable to the imaginary component, but there I was just averaging this much. Just averaging the imaginary part, and here it is some it's there's an extra term here, so it's not the same as IMC but comparable, and it has these nice properties that it still cares about the magnitude differences that in the distribution in the positive and the negative side. It's just getting scaled by what the imaginary component is. Okay, so this is WPLI. If you are interested in its mathematical properties beyond just the description of this, you can read this paper. And the imaginary component, the IMC looked like this. I had shown earlier. If you compare this to WPLI, it will look like that. Similar, but some differences between the two. Okay, so this is weighted PLI. These are all ways for us to measure the relationship between the signal here and the signal at these other electrodes. So the WPLI and the IMC analysis says that the signal here in the gamma range has some relationship to the signals in the central part of the brain, which I didn't see earlier when I was just doing the coherence analysis here. Okay, so I'm going to do one more, which is actually a little bit more involved, and then I'll finish off with Granger causality. At this point, if there are any questions, please ask. Otherwise, I'm going to talk about PPC and then GC. Okay, so no questions means everyone is okay with what I'm saying. So now I'm going to talk about one very popular method in the field called PPC, and it's popular because it addresses this bias that's related to the sample size. Okay, and this is I'm going to tell you where this bias is coming from, and then I'm also going to describe how this method addresses this bias. So one issue with measures such as coherence and phase coherence is that they have a positive bias that depends on the number of observations, on the number of vectors that you have. So the idea in PPC is that you look at a measure that does not depend on the number of observations, and you do that just by looking at pairs of observations at a time instead of all the observations together. So at a time you only look at pairs of observations, and the idea is that if phases are consistently clustered around some mean phase, they on average will have a small angular distance to each other. What does it mean? I mean that if all the vectors, so here I've got a bunch of vectors which are all pointing in the same direction, then if I pick out any two vectors, let's say this one and this one, they will have a small angle between them. And this will be true for all the pairs. So what I can do, given n trials or n vectors, each trial giving me one vector, I can have n choose two unique pairs of vectors. And the PPC is simply the average dot product or the average cos of the angle between them. If they are if the angle is 0, then the value is 1. Otherwise, the dot product is just the cosine of the phase difference. So PPC is simply equal to the average dot product across all pairs, and turns out it provides an unbiased estimate of the square of the PLV, of the phase locking value. And I'll tell you how this comes about in the next slide. So just to make sure everybody understands this, suppose I've got 4 trials and I've got 4 angles then. So each angle here is the phase difference between the two signals. So theta 1, theta 2, theta 3, theta 4. These are all unit vectors. If I was computing the phase coherence, I would just take the average of these 4 vectors. So I'll get some resultant vector. and the magnitude of that would be my phase coherence. Okay, so if I look at this vector, it's pointing here. These two sort of cancel each other out. Well, they don't cancel. I mean, this one would cancel, but this would be a vector like, okay, so the resultant vector would be, I guess, something like this. Just guessing here. So the magnitude of this vector would be phase coherence. The imaginary part here would be your imaginary coherence, IMC. And then if you scale this in a particular way, I guess 3 vectors are positive and 1 is negative. So your WPLI would be some number that will depend on that. What am I doing when I do PPC? I do as follows. So discard this vector and I'll come back to this again. What I do is that I look at the dot product between every pair. So now I've got 6 pairs, force choose 2. So between theta 1 and theta 3, the dot product between this or the cosine of this is just this dotted line. It's the projection of theta 3 on theta 1. This line. Dot product between, so that's F13. Okay, so F12 is just the projection of this theta 1 on theta 2. That's this small vector here. This is the projection. This is so if 2 vectors are orthogonal, it's going to be 0. Otherwise, this is the projection. So this is the dot product. So this is F12. F23 is the projection of 3 on 2, which is this. Okay, so I am computing the dot product between every pair. So I got F13, F23, F24, F34, F14, F12. I guess that's it, right? F12, F13, F14, F23, F24, and F34. So these are the 6 vectors. The average of these is the PPC. Okay, so that's the pairwise phase consistency. So now you might be wondering why we are doing it this way. Okay, so let me try to explain the logic here. So suppose you've got vectors which are truly random. They're all over the place. If this is the case, what do you expect your PLV to be? Come on, at least answer that. What do you expect it to be when they are all random? Phase locking value is the same as phase coherence. If you had got a million of these, what do you expect the PLV to be if they are completely random? Huh? Yeah, it's going to be 0, right? That's what you expect. But the problem is that if you only had a finite number of these vectors, then for each vector here, you may not have another vector that points in the other direction because you have so few. So the average vector may not be very small, even if they are truly random. That is where the PLV has a bias. It depends on the total number of trials. So let's just think about this a little bit better and try to estimate what this bias is going to be. How would it depend on the number of trials that you have, which is n? So for each vector that you have here, I can, so what am I doing? I'm averaging all these vectors. So I'm averaging all the vectors and then I'm taking the magnitude of that. So now let me just divide this vector to its cosine component theta and a sine component. So each vector is cos theta plus j sine. Oops, happened here. Okay. Sorry about that. Not working. Okay, now it works. So I'll discard these changes and come back here. Okay, so let's think this through. Each vector is cos theta plus j sine theta. I'll just call this cos theta 1 plus j sine theta 1. That's my first vector, e to the power j theta 1. And I've got a ton of vectors like these. So this is one vector at theta 1. And the other ones would be theta 2, theta 3, and so on. So what happens when I'm taking the average of all these vectors? I'm essentially doing summation cos theta I plus j summation sine theta I. Correct? I'm just summing the cosines and then I'm summing all the sines and then I am going to look at the magnitude of this whole thing. That is my PLV. I'm going to then look at the magnitude here. After I divide by n here, then the magnitude. This is the PLV. So when I take the magnitude of this, what do I get? So I'll, take the n square here. It's just the square of this term plus the square of this term, and then you take the root, right? Because you have a j here. The magnitude is just this square plus that square and the root. What is that? So 1 by n square comes here. And now it's the sum of cos theta I plus sine theta I root of this. This is my PLV. The root will take care of this. So PLV square is nothing but n square and then the sum of squares of this and sum of squares of this. So let me expand this. What do I get? I get cos square theta 1 plus cos square theta 2 plus da 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 cos square theta n plus all the cross terms cos theta 1 theta 2 plus I guess 2 cos theta 1 theta 2 plus 2 cos theta 2 theta 3 and all these cos terms here, and similarly for sine. Plus all these terms here. Does that make sense? Yes? Have I lost people here or is this fine?
Yes, sir.
This is fine, right? Now notice that there will be n terms here which will add up. So cos square theta 1 plus sine square theta 1 is 1. This is 1. This is 1. And this part here is actually just your PPC. Okay, so the idea is that your PLV square, the phase locking value square, if I now look at this, PLV square is biased because even when vectors are completely random, in which case you expect this whole term to be 0, because the angles are all random, right? So cos theta 1, cos A cos B plus sin A sin B is just your cos A minus B, or cos A plus B, one of the two. Basically it's looking at the phase differences. So it actually turns out to be, sorry, not phase difference. This is the dot product between the unit vectors. So this thing here is actually your PPC. And you expect when vectors are completely random, this term to be 0. But when you compute the PLV, it won't be 0 because there will be n such terms here. So it's actually going to be this. So this is the bias. This is the bias that we have mentioned in the phase coherence. Unless your n is very, very large, PLV will never be 0, even if the vectors are completely random. So the bias in PPC, in PLV or coherence goes as 1 by root n, and this is the proof for that, because the square has this term. So what Wink and his colleagues very smartly did was identify the part which is not biased, this part, and define that is as their PPC. It's actually very, very elegant, very smart. Okay, all you are doing is dividing your PLV square into components that are fixed, that are dependent on n, and whatever is left behind. And this left behind part is the unbiased measure of the square of the PLV. Okay, because you're defining it by not considering this part. So this is why the PPC is equal to, which is the average dot product across all pairs, provides an unbiased estimate of the square of the PLV. If you had a million trials, then the first term would drop out, and you will get uh, the PPC as the square of the PLV. Okay, does that make sense? So instead of PPC, PLV or coherence or any other measure, if you use the PPC, which is also very simple to compute, you will get the same answer irrespective of how many trials you are using. And this is a big step forward, because in neurophysiological data, you can't keep computing millions of trials. You only record for so much time, and you have often like 10, 20 trials or maybe 50 trials at most. And if you're comparing across conditions, let's say hits versus misses, hits 30 trials and misses 10 times, the difference in n is just going to uh, play a big role if you are using a measure like coherence. But you can use PPC, and it doesn't depend on n, because it's a pair-wise phase consistency measure. It at a time only cares about pairs of phase differences. Sorry, phase difference between pairs of vectors. Okay. All right. So in quick succession today, we have done 4 measures. Phase coherence, which we had done earlier. Then we did imaginary coherence. Then we did weighted PLI, and we have done PPC. Okay, and most of the methods are actually built around these only. These are like the major techniques that are used in analyzing connectivity measures. So I will now wrap up the course by briefly talking about Granger causality. And it's actually such a deep topic that you could even have a course just on Granger causality or other causality measures. But I will just give you a very brief outline of this and then I'll close. Before that, any questions on the connectivity measures? Or can I start Granger causality? I hope to finish it very quickly. If there are any questions on connectivity, please ask. Okay, so if not, now the final part that I'm going to talk about is that the measures that I have talked about so far. If I look at uh, coherence between this electrode and that, it's basically just one measure that says what's the phase consistency between the signal here and there at a particular frequency. Unfortunately, it cannot tell me whether this signal here is causing changes in this signal or whether this signal here is causing changes in that signal. There's no causality in any of the connectivity measures. They are all correlational measures. But I am often interested in causal measures. I want to know whether a signal in V1 is causing changes in V4, which would be some feed forward processing, versus some signal in V4 or frontal cortex causing changes in V1, which would indicate some feedback. So this causality is often very important for us because it's important for us to know which brain area causes change in other areas. So we turned to a very popular measure called Granger causality, which was proposed by Clive Granger, and he got a Nobel Prize in economics for his contributions. It's actually a concept that was developed earlier by a guy called Wiener, but it was formalized by Granger, so it bears his name. And the main idea is very simple and is written here. The rest is all math that I will describe. But the main idea is simply this, that if I have two signals, x1 and x2, and I am trying to predict x1 based on its own past values. Okay, so I'm going to say I'm going to predict what x1 is going to be based on what x1 was at some previous time. And so on. So these are called auto-regressive models. In stock exchange, for example, if you look at the trends in the previous few days, you can make a prediction of how a stock is going to be today. So I can make an auto-regressive model here. And similarly, another auto-regressive model for another signal. And that's all fine. However, but if giving past values of y improves my prediction of x, so if I also include past values of let's say y here, and it makes the prediction of x better, that means y has some causal influence of it on x, because providing the past values of y is improving my prediction of x beyond what I can get by using the previous values of x alone. Then y will Granger cause x. Okay, here it's defined in terms of x1 and x2. So let's read this. According to Granger causality, If a signal x1 Granger causes a signal x2, that means that the past values of x1 should contain information that will help predict x2 above and beyond the information contained in the past values of x2 alone. Okay, does this concept make sense? What I'm going to tell you now is just the mathematical formulation of this simple concept. So let's look at the mathematical formulation. So the basic idea can be tracked back to Wiener, as I mentioned, but Granger formalized it, so it bears his name. So what you are doing here is as follows. Suppose you've got two stochastic processes, xt and yt, and you have an auto-regressive model, which means you are able to predict xt based on past values of x, and you are able to predict yt based on past values of y, and you have some error in the prediction, some part that you are unable to predict, which is in this case is given by epsilon and eta. Okay, and then the variance of epsilon here is your sigma 1, and variance in eta is this is capital gamma 1. So this is your standard. I won't talk about how such models are solved. There are standard ways in which you can estimate A and won't talk about so, we were doing we learned about local equations, for example, which can be used to a variety not right now can estimate of A and D easily, and how well your autoregressive model is doing determines what the error is going to be. If it's a good model, it's going to be small. However, now I actually make another way of models where xt depends on not only past values of x, but also past values of y. Same with y, past values of x and past values of y. So in this case also, I can estimate ABCD using some standard equation, standard methods, and then I will have error in the estimate. Uh, now it's sigma 2 and gamma 2. So by the way, a very good reference for this is this Mingzhou's Ding's work, 2006 paper, Ding et al. So if you are interested in the math, this is where what you should read. I am actually using their formulation only. So the main idea here is that if adding y's improves the prediction of, then sigma 2 is going to be smaller than sigma 1. Likewise, if adding x improves the prediction of y, then gamma 2 is going to be less than gamma 1. So I can simply say that the influence of y on x is the reduction, the ratio of sigma 1 to sigma 2. Remember, this is going to reduce and the influence of y on x. Okay. This is sigma 1 equal to sigma 2. Then this is 1, LN1 is 0. So the Granger causal influence is just sigma 2 is less than sigma 1 in some suitable statistical sense, then yt is said to have a causal influence on x. Okay, does this make sense? This is very intuitive. Are there any questions on this? So all you have done is you have set up a causal autoregressive model, and this is also a autoregressive model, but you are using past values of both x and y. And if this reduces, so that this is smaller than that. Then you say y has some causal influence. So f of y given x in this case is ln of sigma 1 by sigma 2. If there is a big causal influence, then this is going to be much smaller than that, and this ln is going to be a big number. Okay, that's it. That's Granger causality in the time domain. And now I'm just going to finish off by describing Granger causality in the frequency domain. It's actually a tricky concept intuitively, because when I talk about frequency domain, I'm just talking about sinusoids, right? So I'm talking about a 40 hertz signal in this part of the brain and another signal in that part of the brain. And if I'm just looking at sinusoids, how can I actually talk about, whether this one is causing that or that one is causing this, right? I mean, this is conceptually trickier um, because, just because one is phase lagged or phase leading doesn't tell you about the direction of causality. So if the vectors point in one direction in the coherent sense versus other direction, just from these vectors you can't say whether one is causing the other. That this one is causing that one after a huge phase, so that the vector is just pointing in different directions. Just by this you cannot determine causality. So you could ask, hey, how am I going to determine causality just with sinusoids? So intuitively, it's a difficult thing to understand, but as we'll see, mathematically, this will make sense. And that is the spectral Granger causality that I'm going to describe now. Okay, so very last thing. So please pay attention. We'll be done soon. What you are doing here is you are writing the previous equations in a matrix form. Okay, this equation you want to write in a matrix form, but you have got xt and here you have got xt minus 1, xt minus 2, xt minus 3. How do I write it in a matrix form? I will do that by writing it in an operator form. So I determine, say L is an operator, it's a lag operator. When I operate on xt, I get xt minus 1. So xt minus 2 is just L square, and so now would be xt equal to infinity j. T minus j is just L to the power j xt. So now you can bring the terms on one side and isolate xt, and you end up getting something like this. Okay, so these are polynomials. It's going to be 1 minus a2j L plus minus a22 L square minus L23 L cube and so on. Don't worry about this as of now. So these are polynomials A, B, C, D that it's a 2 cross 2 matrix, which is now applied to xt and yt, and this will yield the error terms on this side, epsilon and eta. Okay, so this is nothing but the same equations here written in a lag operator form. So this is actually a complex thing in the time domain. However, turns out the lag operator, which is just a shift in the signal, is very well represented in the frequency domain. You just multiply the signal with this phase change, because the shift in time domain corresponds to a multiplication in in the change in the phase domain. So we did this when we were doing Fourier transform, that to get a shifted version of the signal, all you have to do is multiply the signal with some phase. So that is where this term comes about in the frequency domain. So in the frequency domain, this whole thing turns into this A, B, C, D, which are given by these four equations. Okay, so if I give you an omega, you can actually quickly compute that. Remember, A, B, C, D is something that coefficients that I can get from Yule-Walker equations or some other way. So I actually can get this matrix in the frequency domain if I specify omega. Okay, so what I'm seeing here is just the frequency domain representation of these time domain signals and the errors. Okay, and this thing is called the matrix A, coefficient matrix A. Okay, so that's that. This is just a formulation in this of the same thing in the frequency domain. Now I can invert A and write X and Y as as this H times the error terms, where this is A inverse. Okay, and if it is invertible, then these can also be very easily obtained. This is A, B, C, D. Uh, A is A, B, C, D. So the determinant is AD minus BC, and then the inverse is going to be similar. It's I think BA minus what is it? Yeah, D minus B minus CA. It's easy to work this out. You can work this out that H coefficients are just going to look like this. Okay, so now I have written X and Y in terms of the matrix H and the error terms E. Now comes the only involved part here, which is the computation of the spectral matrix S, which is nothing but the auto spectra along the diagonals and the cross spectra here. So this is a 2 cross 2 matrix, which is x conjugate here, y conjugate here, and x y conjugate here, and y x conjugate here. The expected value of these. Okay, so how do I get that? How do I get the spectral matrix? Well, it's straightforward. The spectral matrix, which is just this xy multiplied by its conjugate, which will give you this. And this vector is just h multiplied by this, right? So this is a column vector. It's 2 cross 1. This is a vector 2 cross 2. This is a 2 cross 1. So when I look at its conjugate, it's just going to be x, this, and its conjugate here, and then the conjugate of h. So h, this, and this thing is nothing but ex star, ex, the auto and the cross spectra in the frequency domain. Okay, maybe I didn't explain this properly, so let me try this one more time. I've got XY matrix here, and I'm interested in finding the spectral matrix, which is just a 2 cross 2 matrix containing the auto and cross spectra. That's it. To do that, I just need to look at the expectation of this matrix with its conjugate, like so. But this matrix is given by H multiplied by the error terms, right? So the conjugate of this is just, so it's just this conjugate multiplied by that conjugate. So it's going to have the the EX conjugate omega EY omega and then H conjugate here. Now this will become a 2 cross 2 matrix, and its expectation is just this. And this is actually, this sigma 2 and gamma 2 is actually the same as what you had here, this sigma 2 and this gamma 2. Because the energy of this in the time domain is the same as the energy computed in the frequency domain. This is the Parseval's theorem that we had done. Okay, so the variance where you square, it's the same as the energy. You're looking at the energy of the signal. So my spectral matrix is just going to be H multiplied by this thing here, multiplied by H transpose, where this is what I had earlier, sigma 2 and gamma 2 defined here. Okay, so why did I do it this way? Why did I do it this way? I did it this way because now I can think of the first element Sxx omega. Remember, this is a 2 cross 2 matrix. This is a 2 cross 2 matrix. So it is Xxx, X, Xy, Syx, Syy. So if I look at the first entry, which would then depend on Hxx, and then you multiply it with this and multiply by that, it will become this whole term. Okay. So now consider, now you might be wondering, why am I doing all of this to begin with? I was quite happy here. Why did I compute the spectral matrix? Because I want you guys to think of the intuitive meaning of what is going on here. Let's consider a case where this cross term, this is the cross between the two error terms. Okay, this is epsilon here. Let's consider this to be 0. So this term here goes away. So I'm looking at two terms here, Sxx given by this plus that. What does this mean? The first term doesn't depend on y at all. This is the intrinsic part. The energy of the signal here is decomposed into one part, which is intrinsic because it doesn't depend on y, but there is another part which does depend on y. The first term is viewed as an intrinsic part, involves only the variance of the noise term that drives the xt time series, this one. The second term, which is viewed as a causal part, involve only the variance of the noise term that drives yt. This. See that? This is the noise term that is driving yt. It's the eta, the variance of eta 2. So the energy, the spectrum of X actually has an intrinsic component and a causal component. So my spectral Granger causality, the influence of Y on X, is simply the total energy divided by the causal part, is this term here. Okay. And f of X given by Y is this. Oh, sorry, not this part. It's actually this part. Sxx is this thing, and this part is the self term. So the causal influence of Y on X at a frequency omega is the total energy, the spectrum here, divided by the intrinsic part, this part. If the intrinsic part explains the total part completely, then Y has no contribution. And this will be 0. Otherwise, Y does have a contribution, and this part, the numerator is going to be larger than the denominator, and this value is going to be slightly larger. Okay, so this is a spectral Granger causality. It is difficult to explain. I mean, usually we spend a whole class on this. Rangarajan, who's an expert, our director, he's an expert in Granger causality and these sort of measures. So he used to take this class back in the days. Um, and he would take an entire hour to explain this and other concepts also. So it's a very abridged version of the whole thing. You might be wondering why there's a tilde here. This tilde is nothing but a slight modification that you do on H if your this term here is non-zero. Okay, it's just a very clever pre-multiplication so that you can still divide this autospectra here as a intrinsic and causal component even when this part is non-zero. I'm skipping the details. You can find the details in Ding et al. 2006. But that just changes the formulation from H to another term H tilde, which has this epsilon and sigma both. Okay, if this is set to 0, then H tilde becomes the same as H. So this is spectral Granger causality. You have got a program here which computes the Granger causality. Display causality.m, and the M var, this is one method that is used to compute the coefficients. There's also other connectivity measures, directed transfer function, forgot what PDC was. So these are involved concepts. These are actually excellent topics for you guys for your grant proposal. You could try to understand a partial directed coherence. What these are, conceptually very difficult to understand also. So this is actually quite involved what I'm showing right now. But if you just run this, it's a short code. It will generate plots that look like this. So this was my weighted PLI, and this is the outflow of Granger causality. This is the causal information from this to that. And you will similarly have an inflow, which will tell you how much is the influence of these electrodes to that. Okay, so this plot actually shows that the occipital areas here actually causing some changes in the central areas. Okay, folks, and with that we are done. So I covered a lot of stuff today. For people who are seeing this for the first time, this may be quite daunting, but if you read and play with the codes that are provided, this will fall in place. The only thing that we have missed in this course this time are some pre-processing techniques such as independent component analysis or principal component analysis. Usually, this takes 2-3 classes more. But there's another course that is being offered by Rishi and Arun. They cover part of this. So I'm not going to do that. So that's it. I'm done. I'll stop recording.